So, welcome to the sixth lecture, which is on two types of surface dependent properties, namely the physical and the chemical. In the fifth lecture, we talked about overall classification of surface dependent properties. In fact, we started discussing from how actually, what do we mean by engineering properties and how do we define them. And subsequently, we went into those classifications and talked about various types of surface dependent mechanical properties. We now need to discuss two other major classes which are of consequence, which have influences on various engineering applications. And these two are the physical and chemical properties related to the surface. So, the distinction arises purely from the fact that the activation is coming from either chemical or from physical forces or physical types of activation. So, if you now look into the slides, the very first one, since we are discussing physical properties, so one of the foremost thing that we need to talk about is the topography. I probably did mention in the last lecture that no matter how careful you are, when you synthesize any solid by either a solid state or a liquid to solid or vapor to solid kind of transformation, the surface will definitely have certain degrees of asperities. In fact, the surface that we generally refer to as a very smooth and flat surface, if you bring it under just a simple magnifying glass or maybe a microscope, would definitely reveal certain levels of asperities. For example, you can see here that this is a cold rolled steel sheet, and when you actually the sheet comes out of the roll, it appears very shining, and normally you would not expect that the surface can have such dents or certain surface deformation marks. And these deformations actually, or this kind of dents actually could be just hardly a micron, even less than a micron depth. On the other hand, the steel sheets which are coated with zinc and applied for car bodies and various other applications, or even painted on top of that, even they also will have certain roughnesses, and the typical amplitude of these roughnesses could be again a few micrometers, if not more. So, topography essentially is the description of the surface quality in terms of the waviness or various kinds of asperities possible onto the surface. And there are three characteristic features generally one talks about while describing the topography or topology of the material. Lay, which essentially describes the surface pattern due to the direction of various deformation or synthesis processes which preceded the formation of that particular solid. One can the next important part is the surface roughness, which actually arises primarily when the material is machined at some point of synthesis or fabrication, and the grit size of the grinding wheel or the depth up to which the abrasives would have actually polished the surface, or cutting tool would have cut the surface, leaves behind certain marks of roughnesses. And then you also can develop waviness, which essentially is arises because of the various surface contour variations of the counter face or vibration and chatter happening during the fabrication process. So, whenever we have such topological or topographical variations and we need to actually measure them, then we employ one of these profilometers, which could be a contact like here, or can be a non-contact profilometer. So, in a non-contact profilometer, we generally we follow the reflection profile, and the surface, if it has certain levels of waviness or roughness, then will definitely show or different kinds of contour. Imagine a surface or a solid component which is freshly machined, and when you machine, then the cutting tool actually moves over the surface and removes material by application of mechanical forces. Or for example, you think of a solid surface which is freshly ground through grinding wheel or polished using certain abrasives. So those grits onto the grinding wheel or the abrasive particles, their size and geometry would leave such asperities onto the surface. But if this amplitude is submicron, less than a micrometer, then you don't actually distinguish them by your naked eye. So you essentially tend to see a very flat and shining surface. But if you take it under the microscope, then you see certain levels of roughnesses, which could be average roughness, which could be described in terms of root mean square roughness or maximum roughness. And this maximum roughness, the total amplitude could be fairly large, but of course these are randomly occurring, not uniform. So in order to measure these roughnesses, as I said, we use contact profilometer. We can use also non-contact profilometers like optical white light based profilometer or laser light based profilometer, even atomic force microscopy, where the if it's not in a tapping mode, the tip actually will not even touch the surface, but still be able to measure the forces onto the surface when it is brought to very close proximity to the solid surface that we are investigating. Color is a very important engineering property. In fact, aesthetics to a large extent depends on the color and the ability to reflect light. But we must realize that the color that we see essentially is a reaction or coming, the activation is the incidence of light on it, which could be white light, a combination of various wavelengths, typically in the range of about 350 to about 700 nanometer wavelength. And in that kind of a range, depending on the surface nature and its chemistry or the composition, we tend to absorb certain wavelengths more than the rest, and as a result, we see not a white or a composite color of the surface, but a typical color. And so these colors, the manifestation of these colors will depend upon what kind of wavelength we are prone to absorb or scatter more, and essentially that would determine. In fact, when we have 2 or 3 very dark colors or very monochromatic colors incident onto the surface, then this combination of these colors actually can create a sensation which is going to appear as dark or black. So it depends on actually the receptors that we have in our eye, which is sensitive to different types of wavelengths. So what receptor is active for a particular view, and what wavelength is actually able to excite those receptors for a particular incidence. So in fact, we tend to be always, there's a common saying, all of us are aware, all that glitters is not gold, but actually it's that glittering property or the reflection or reflectivity property that determines or that actually is the reason why gold is so popular and so precious for all the ornaments and various other decorative purpose. But the fact remains that gold actually is able to reflect light over a wide range of wavelength, incident wavelength. So that's why it's always glittering. Compared to that, there are other metals which are not as efficient as gold, and that's exactly the reason why gold is so precious as ornament. For various purposes, for example, the surface of a mirror, you would not like to have a situation which is like this. If you have a lot of roughness onto the surface, then the incident beam will get scattered in all directions, and then the reflected light will have certainly not be able to gather all the scattered rays, and not only the image could be distorted, but more importantly, the intensity of the image that you will create will be weaker or poor. So reflection is a property which is very much dependent on the surface topology and topography, and hence that's something we need to know before we design a surface for particular reflection, including creation of a mirror surface. So until now, the entire effect was due to the reaction to an excitation coming from optical rays, and instead of emitting light, we actually can even emit electrons, and this emission can happen because of multiple possibilities of excitation. Over here, when we talk of thermionic emission, we are talking about a situation where we apply very high amount of potential difference and current, and as a result of which certain elements, for example tungsten or a compound called lanthanum hexaboride LaB6, actually can emit very high density of electrons from the surface. And these electrons have their own utility. We make use of them as, so this is a gun, a cathode ray gun, or there are multiple other applications. But what is even more important is that all the solar cells actually would also like to make use of such properties of either organic or inorganic substances, which actually can create electron on hole pair and on a particular photosensitive coating, and those separated electrons can be either stored or carried away to form current, and that gives us energy. So thermionic emission is a phenomenon or a property which is dependent upon the ability to emit electrons from the surface due to excitation purely which is of thermal in nature. We can also have field emission phenomenon where electrons are emitted because of the application of field, electrical field, and such kind of a phenomenon is utilized in, for example, this scanning electron or transmission electron microscope, where we have this large column, and the primary part, the stream of electrons is emitted from this electron gun, which either could be such due to such thermionic emission, what we just saw coming from tungsten wire or LaB6 compound tip, or it can also come from due to field emission happening because of large electron large potential difference created at the tip. Electrons can be emitted also because of excitation coming from optical ray. In some metals, if we have, or particularly on some because of certain coatings, we actually can see a situation where incident wavelength can raise electrons from the valence to conduction band, and these electrons now are ejected because of the excitation coming from the incident light, and these electrons are captured and then carried away, and which creates a current, and that's what we call photoelectricity or photoelectric effect. Wettability is a very important phenomenon. We did discuss this in one of the earlier lectures. Look at the possible scopes of application. I mean, we are all aware or would have possibly used the non-sticky frying pans, and similarly we use raincoats or umbrella or wax paper cups and so on. All these are basically hydrophobic surfaces under different conditions. This is under high temperature condition, but this is in room temperature. And in all these cases, we don't allow the water to stick to the surface. So we don't want anything like this. What we want is somewhat like this. That means the water droplet should not spread easily onto the surface. And this is made possible, can be made possible either by changing the surface contour, the topography of the surface by creating certain patterns, or changing the chemistry so that the surface tension is modified, as a result of which the contact angle is very high. When we need to actually glue two different surfaces, two different dissimilar surfaces, the adherence of these two different surfaces, which will largely depend upon the adhesive forces that we can create either by themselves. The two surfaces can have a natural tendencies of adhesion, or we can apply material in between, for example, a glue or a gum, which actually can lead to chemical adhesion. So, adhesion can be mechanical in nature or chemical in nature, but nevertheless is very important for us to be able to join two different solids which are of dissimilar nature. And there are examples in nature. For example, this flower actually is a bright example of how dispersive adhesion can happen because of the presence of certain chemicals at the tip of this bud, and that's how the pollen actually can get attached to the insects, and then subsequent biological phenomenon can take place. When we are talking about dissimilar, then we talk of adhesion, and when we talk of similar molecules or species, then the bonding between them is described as cohesion. So, the cohesive forces also is very important, because they eventually will govern the meniscus of a fluid or a bulk of liquid, or the surface tension that's manifested, and even the capillary action. So, for example, if you have two water droplets placed side by side, and if they either due to mechanical vibration or for some reason, if they are able to actually come in close contact, then they'll immediately merge and make a bigger droplet. And this kind of capillary action happens because of the forces of cohesion. All these adhesion, cohesion, the topography, the photo emission, photoelectric emission, thermoionic emission, all these are surface dependent properties of solids due to various kinds of activation coming from different types of physical forces. And now we are going to examine what's going to be possible for similar properties which are dependent on activation coming from chemical forces. For example, the most common thing whenever we talk of chemical actions or chemical processes, what immediately comes to our mind is the chemical reactivity. And we are aware from our high school physics that the elements which are farthest apart in terms of their location in different different periods, so they basically will have very large tendencies of reacting with each other. So, for example, francium is the most reactive metal, and it is in the first period, and then we have fluorine, which is one of the most reactive nonmetal, which is the most reactive nonmetal. So, whenever you expect something at the too far apart in the periodic table, and they are likely to actually react with each other very strongly. So, but then when they react, this reactivity of a solid, I mean, this is about the pure elements, but when you talk of solids, when two solids come in contact with each other, there could be chemical forces acting between them, and it could be a solid solid, it could be a solid liquid or a solid gas, and eventually the surface is likely to undergo certain chemical reaction or transformation depending on its tendency of such chemical reaction. Take the example of pure iron. If you leave it in the open, we all are aware, we all have common experience that it develops certain compounds forming onto the surface, which we call rust, brownish color, and this rust actually grows with time, even if you don't do anything at all to the material. It grows because it reacts with the atmosphere, forms certain hydroxide, and these hydroxides are fairly porous and structurally very different than the underlying substrate, and because of which the rust or the compound actually spalls off the surface and exposes fresh one, and that's how this process of degradation continues or the rusting continues. So, any solid, if it is polar in nature, will always have a tendency of dissociating. We are aware that essentially this it can actually it can give up electrons and then get oxidized, goes into the oxidized state or oxidation state, or if it actually acquires electrons, then it gets reduced. And that's how whenever electron transfer takes place between two different species, one gets oxidized, the other gets reduced, and in the process we possibly end up forming a compound. And this is how in most of the cases the undesirable phenomenon of oxidation takes place. And this, please remember that this oxidation is much more aggressive at high temperature. When the mass transport is faster, when the growth rate of these kind of oxides onto the surface of a metal or any other solid for that matter is much faster. And so one doesn't need to always worry about whether the element belongs to group 1 or group 2 or something. First thing is that whenever we have elements which are farther apart in the periodic table belonging to in terms of their classification under different groups, they are likely to react. So, from the atmosphere, if we pick up certain cations, maybe oxygen, maybe chlorine, or maybe some other kind of anions, and if we have a metal or for that matter other solids which is ready to offer certain cations, so these anions and cations are likely to react immediately depending on their tendency of reaction, and this rate of reaction or the degree of such reaction would be much higher at higher temperature, which is what happens in case of oxidation. And this leads to gradual conversion of the solid into a different form, which is mostly undesirable, and we need to prevent them. So, in order to first be able to prevent, we first should realize how this degradation is taking place. And such a degradation, as we just saw in case of oxidation, is essentially a chemical degradation process. A similar thing can happen in terms of corrosion, and this is what I was just now explaining in terms of rusting. And nobody wants the iron should get rusted, but this is also something that is unavoidable. In fact, in the lighter vein, one can say that this is how Mother Nature actually preserves its precious resources. So, nobody gives you iron in its in the native form. We all get oxides or sulfides or various kinds of ores and minerals, and then using our imagination and scientific knowledge, we are able to win the metal value from those oxides or sulfides or nitrides, and then we use. But if you're not careful enough to actually protect them by way of either coating or some such exercise, then Mother Nature sees that you are not caring enough for the metal, so it converts the metal into oxides and take it back to the condition under which it can be very easily saved and stored forever. And this happens because of one very important reason, and that's what I wanted to actually point out now. I did mention earlier that all systems in the universe always tends to minimize its Gibbs energy, because that's how it can improve its stability. In order to actually reach that stabler form, we have to weigh the options which is more stable. Like I was describing the example between iron and iron oxide, and if you have these two lying side by side in open atmosphere, obviously according to the thermodynamic conditions, the oxide would be stabler than the pure metal. And that's exactly the reason why there is a natural tendency always for any metallic systems to undergo either corrosion or oxidation, which essentially are very similar electrochemical processes. Only oxidation occurs usually occurs at high temperature, whereas corrosion can happen in the presence of an electrolyte at room temperature. But whenever we have metals of dissimilar nature, for example, if you look at this series here, these are called galvanic series, and they are actually created in terms of the galvanic potential or electrochemical potential of these metals. And these So in this series, actually, they are arranged in terms of their electrochemical potential, and it clearly shows that the metals which are high above into this series are much more reactive, and that's why they are called anodic, whereas the ones which are at the bottom of the series are cathodic. So these metals which are at the top of the series are very prone to donating electrons and get oxidized, and if there is an electrolyte which actually can conduct either the electrons or the species, the ionized species, then it reaches the other end and donates the electrons, or the electrons are acquired by the cathodic part of the cell, and that's how the transfer of electron leads to gradual degradation of these metals into another form. In order to prevent this, we actually need to create a passivation layer, and this passivation is possible only when we actually create an oxide layer. Normally, we don't want to convert a metal into an oxide, but in certain cases, we actually prefer to create an oxide layer. Only difference is this oxide layer actually has to be very adherent and stable and non-porous, so that further ionic transport across this oxide is prevented or stopped, and hence the process actually stopped, or and further degradation cannot take place. So catalysis is another such phenomenon. I mean, it's very simple for us to understand the way the catalysis works. That if you actually imagine a hump like this, such a big hump, so it actually shows that you have a large barrier to cross. So instead of this big hill, if you have smaller hillocks to actually cross, which is going to be much easier, and that's exactly what happens when you do catalysis. So essentially, you need certain extraneous agent which act as catalysts, which actually accelerate the process, and this acceleration of the process is called catalysis. But on the other hand, if we don't want such reaction to take place, then we apply the opposite, which are called inhibitors, which actually reduces the rate of the chemical reaction. Fine. So now it's time that we sum up. So just like the way we discuss the various surface dependent properties under mechanical activation, here we discuss surface dependent properties under physical and chemical activations, and we try to understand what are the origin of various surface dependent properties. For example, when you excite the surface with a certain photon, if that surface is photosensitive enough, it can emit electrons, and that's what is known as photoelectricity. On the other hand, if you expose a surface to certain chemical reagents or certain ions, and if it leads to chemical reaction and gradual formation of a compound, then that is corrosion, and that's essentially through a chemical activation. So these surface dependent properties of coming from physical or chemical activation are very important, because as we discussed in the previous lecture, that they actually determine the life, the reliability, the safety, the utility, overall utility of the component in the long run. We should be aware of the various kinds of equipments and protocols used for assessing the surface dependent properties. For example, how do we measure corrosion property, how do we measure physical properties, and so on. Some of these properties are intrinsic in nature, but not always. So the activation, something can happen from within, so we call them intrinsic, or something happens because of extraneous influences which are extrinsic. So both kinds of varieties are possible in these categories. And what actually we should now try to focus upon in the future lectures is how we can actually tailor the surface properties by way of changing the microstructure and composition of the near surface region. So we need to discuss a little more of fundamentals about the strengthening mechanisms of various types, both for metals and non-metals, before we start discussing the processes which are typically called surface engineering techniques. But before that, in the next lecture, we'll discuss about classification of various surface engineering approaches. Thank you very much.